Finally, we're going to talk about support vector machines, which is a very advanced way of clustering or classifying higher dimensional data. So what if you have multiple features that you want to predict based off of? SVM can be a very powerful tool for doing that, and the results can be scary good. It's very complicated under the hood, but the important things are understanding when to use it and how it works at a high level. So let's cover that now. Let's talk about support vector machines, and this is a fancy word for what actually is a fancy concept, but fortunately it's pretty easy to use. The important thing is knowing what it does and what it's good for. So support vector machines, it works well for classifying higher dimensional data, and by that I mean lots of different features. So it's easy to use something like k-means clustering to cluster data that has two dimensions, maybe age on one axis and income on another. But what if I have many, many different features that I'm trying to predict based off of? Well, support vector machines might be a good way of doing that. Mathematically, what it can do is find these higher dimensional support vectors, that's where it gets its name, that define these higher dimensional planes that split the data into different clusters. And obviously the math gets pretty weird pretty quickly with all of this. Fortunately, the scikit-learn package will do it all for you without having to actually get into it yourself. Under the hood, you need to understand, though, that it uses something called the kernel trick to actually find those support vectors, and there are different kernels you can use to do this in different ways. All sounds very fancy, but again, the main point is you need to use SVMs are a good choice if you have higher dimensional data with lots of different features, and there are different kernels you can use that have varying computational costs and might be better fits for the problem at hand. And also I want to point out that this is a supervised learning technique. So we're actually going to train it on a set of training data. And we can use that to make predictions for future unseen data or test data. So it's a little bit different than k-means clustering, and that k-means was completely unsupervised. With a support vector machine, it is training based on actual training data where you have the answer of the correct classification for some set of data that it can learn from. Okay, so SVMs, useful for classification, clustering, if you will, but it's a supervised technique, okay? Keep that in mind. So one example that you often see with support SVMs is using something called support vector classification. And the typical example used is the iris data set. So one of these sample data sets that comes with scikit-learn is called the iris data set. And what it is a classification of different flowers, different observations of different iris flowers and their species. And the idea is to classify these using information about the length and width of the petal on each flower and the length and width of the sepal of each flower. And a sepal apparently is a little support structure underneath the petal. I didn't know of that until now either. But you have 4 dimensions of attributes there. You have the length and width of the petal and the length and the width of the sepal. And you can use that to predict the species of an iris given that information. So here's an example of doing that with SVC. Basically, we have sepal width and sepal length projected down to 2 dimensions so we can actually visualize it. And with different kernels, you might get different results. So SVC with a linear kernel produces something like this, it turns out. And then there's a linear SVC method as well, also with a linear kernel that produces a result like that. And you can also use polynomial kernels or fancier kernels that might project down to curves in 2 dimensions. So you can do some pretty fancy classification this way, right? So that's an example. Again, these have increasing computational costs, and they can produce more complex relationships. But again, it's a case where too much complexity can yield misleading results. So you need to be careful and actually use train tests when appropriate. Since we are doing supervised learning, you can actually do train tests and find the right model that works. Or maybe use an ensemble approach, right? You need to arrive at the right kernel for the task at hand, and for things like polynomial SVC, what's the right degree of polynomial to use? Even things like linear SVC will have different parameters associated with them that you might need to optimize for. So it'll make more sense with a real example. Let's dive into some actual Python code and see how it works.